Alright, welcome back. Still on homework number 1. Problem number 2. Homework 1 is associated with properties, phase diagrams, and equations of state, and ideal gas stuff. Chapters 1 and 4 out of Koretsky's thermodynamics book. So the next homework problem is straight out of Koretsky's book, 1.5, which is conceptual question. Now it says, consider a binary mixture of a light gas A with mass Ma. Okay. So we have A here, A. We have B here, B. Okay. This has mass. Each molecule, or B, has a mass. Each A has a mass, but this one is bigger. So the mass of B is heavier than the mass of A. They're both at a certain temperature. What does the mean squared velocity, average, of the two species compare? Which species on average moves faster? Okay. Let's see here. Okay. So, what do we have here? Now, again, in terms of, what I'm looking for in a problem is, you structure your problem right. So, in this case, it's good to draw a picture. It's good to write down everything you know. But now we need to explain things. Okay? So, we're thinking about what it's a mean squared velocity. Okay, so we need to recognize, where does mean squared velocity really come into play? What's important about it? And, well, we remember that this is associated with kinetic energy, okay, which is associated with temperature. And really, temperature itself is only a function of kinetic energy slash mass and mean squared velocity. Now, however, it is both. Okay. Now I have to point out this has nothing about an ideal gas. So I really have MB and MA squared. So KE is equal to 1/2 MV squared. Okay. Which is equal to KT3 halves. Okay, so that's what we have. Okay. Now the temperature is the same. The Boltzmann's constant is the same. The 3/2 is the same. The 1/2 is the same. So really, what I have is 2 MV squareds. Okay. So because the temperature is the same, the kinetic energy is the same. Now that doesn't mean this velocity is the same, it just means the kinetic energy is the same. And so what I have is I basically have MAV, that squiggly here for the velocity, squared A equals MB V squiggly squared B. Okay, because their kinetic energies are equal. Now based on that, okay, well, this one is bigger, right? Okay, so I have, let's just say I have, a normal times a normal and equals a big, okay, bigger than normal. What does VB squared have to be to make these equal? Does that it's either smaller, normal, or bigger? Well, let's see here. Let's say normal is, let's give normal a real number like 3, and we'll give this other normal a number like 4. So 4 squared is 16. Okay. Now this mass is bigger. Let's say it's 5. Doesn't say how much bigger, it just says it's bigger. Okay, it's 5, and now I have a velocity squared. Okay, so I have some v squared. All right. Well, this is bigger than this. And so what does this have to do to keep this constant? Be smaller or bigger? It has to be smaller. Okay. By at least some amount. You know, what amount? Who knows? But by some amount. Some fraction. Because I'm going to have a normal number divided by a big number. If I move this over, I'm going to have 3/5 in this case, times 4 squared equals b squiggly squared. Well, because it's smaller, I'm always going to have a fraction. I'm always going to have a percentage. I'm always going to have a smaller amount out of the big amount. Okay? So my velocity squared always has to be smaller for case B. Okay? And so, because, you know, the velocity is smaller, okay, well, it's moving slower.